Chapter 1: Electromagnetic Fury in the Sky. For 5 critical days, between November 4 and November 9, 2025, something extraordinary unfolded in the heavens. Most people went about their daily routines, unaware of the cosmic drama taking place 93 million miles above their heads. Our parent star unleashed a chain of electromagnetic eruptions so immense that solar observatories around the world went into maximum alert. These weren't minor disturbances. This was a storm of truly epic proportions. The active region, labeled AR4274, became the focal point of the international scientific community. This cluster of sunspots displayed a twisted, chaotic magnetic configuration, the kind that makes solar physicists frown and ready their instruments. The magnetic tension stored in that region was like a spring wound to its limit, waiting to snap. And when it did, the release was nothing short of spectacular. On November 4, precisely at 12:34 Universal Time, the first major flare erupted. Satellite sensors immediately classified it as an X1.8, one of the most intense categories of solar explosions. To put that in perspective, an X-class flare releases as much energy as 1 billion hydrogen bombs detonating simultaneously. The electromagnetic radiation crossed interplanetary space at the speed of light, reaching Earth in just 8 minutes. When that surge of X-rays and extreme ultraviolet radiation struck our upper atmosphere, it instantly ionized the ionosphere across the entire sunlit hemisphere, knocking out low-frequency radio communications worldwide. But that was only the beginning. Less than 12 hours later, when many thought the worst had passed, the sun roared again. Another massive flare, this one classified as X1.0, burst from the same active region at 12:14 a.m. Universal Time on November 5. Operators of satellites in low Earth orbit began noticing anomalies in their navigation systems. Airline pilots flying polar routes were instructed to alter their flight paths, descending to lower altitudes where radiation exposure was less severe. Then came the so-called smaller sisters, though smaller is a relative term when it comes to solar explosions. An M7.4 flare erupted later on November 5th, followed just hours later by an M8.6. The flare classification scale is logarithmic. An M-class flare is 10 times weaker than an X-class, but still powerful enough to wreak havoc on technology. These M-class events can disrupt radio communications across entire hemispheres, degrade GPS accuracy, and cause power transformers to experience dangerous voltage surges. Each of these solar flares came with something even more dramatic and dangerous: coronal mass ejections, or CMEs. Imagine colossal clouds of superheated plasma, each weighing billions of tons, hurled into space like cosmic cannonballs. These magnetic structures, often larger than the planet Jupiter, are star-borne projectiles shot outward from the Sun. The first significant CME left the Sun's surface around 10:53 p.m. Universal Time on November 4, directly linked to that M7.4 flare. NASA's computer models, fueled by data from multiple solar observatories, estimated its speed at between 680,000 and 870,000 miles per hour. Let that sink in. Nearly 5 million miles per hour. That's about 0.5% of the speed of light, fast enough to travel from Earth to the Moon in under 2 hours. What made this event truly unsettling wasn't just its magnitude, but its trajectory. The ejections weren't flung randomly into space as they usually are. These were aimed straight at our planet. Scientists at the Space Weather Prediction Center in Boulder, Colorado, watched trajectory models with growing concern. Simulations clearly showed Earth in the direct line of fire. The impact was inevitable, only the timing remained uncertain. The 93-million-mile journey from the Sun to Earth took roughly 2.5 days. During that time, scientists tracked the CME's progress through interplanetary space, drawing on data from the heliospheric satellite fleet. They watched the immense magnetic bubble advance, expand, and evolve as it traveled. With each passing hour, tension grew. How severe would the geomagnetic storm be? Would satellites be damaged? Would power grids on Earth withstand the impact? The answer arrived dramatically at 5:17 a.m. Universal Time on November 7. At that moment, the leading edge of the coronal mass ejection slammed into Earth's magnetosphere, the invisible magnetic bubble that shields our planet. The collision was instantaneous and violent from a geophysical standpoint. Magnetometers at research stations across the globe recorded a sudden jolt in Earth's magnetic field, as if the planet had been struck by an invisible hammer. The solar wind, a steady flow of charged particles streaming from the Sun, usually moves at about 250 miles per second by the time it reaches Earth's orbit. It's like a gentle cosmic breeze. But when the CME arrived, that breeze turned into a hurricane. The wind's velocity doubled instantly, exceeding 500 miles per second. Some monitoring stations even reported peaks as high as 530 or 560 miles per second during the storm's fiercest moments. At the same time, the interplanetary magnetic field's intensity, which normally fluctuates around 5 to 7 nanoteslas near Earth, spiked dramatically. Sensors recorded readings as high as 33 nanoteslas, nearly 5 times stronger than usual. Yet magnitude alone wasn't the key factor. The orientation of that magnetic field would determine how severe the geomagnetic storm would become. This is where physics turns both fascinating and alarming. The interplanetary magnetic field carried by the solar wind has a crucial vector property known as the BZ component, describing whether the field points northward or southward relative to Earth's magnetic field. When BZ points north, matching Earth's field direction, the two magnetic bubbles repel each other. The magnetosphere remains mostly sealed and protective, deflecting incoming charged particles. But when BZ turns negative, pointing south, the physics shifts dramatically. Under those conditions, the interplanetary and terrestrial magnetic fields link through a process called magnetic reconnection. It's as if two opposing fields temporarily fuse, opening gateways through which solar particles can pour directly into Earth's magnetosphere. The shield cracks open, and the solar wind's energy floods into near-Earth space. During the storm of November 7, BZ began fluctuating wildly between positive and negative values. Then, at 9:30 p.m. Universal Time, it plunged to negative 14 nanoteslas, strongly southward. In space plasma physics, that's the perfect setup for large-scale magnetic reconnection. The gates swung wide open. A torrent of charged particles, mostly protons and electrons, accelerated to relativistic speeds, rushed into Earth's magnetic field, streaming along its lines like invisible highways toward the polar regions, where the fields converge and dip into the upper atmosphere. There, at altitudes between 60 and 250 miles above Earth's surface, these high-energy particles collided with atoms of oxygen and molecules of nitrogen in the ionosphere. Each collision transferred kinetic energy, exciting those atmospheric atoms to higher energy states. When they returned to their ground states, they released that energy as photons, visible light in colors unique to each element. Atomic oxygen, around 60 miles up, produced bright green light, the most common auroral hue. Higher up, above 125 miles, oxygen emitted deep reds. Molecular nitrogen contributed blues and purples. The result was that ethereal spectacle we know as the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. Earth's geomagnetic response was rapid and increasingly intense. The KP index, a logarithmic scale from 0 to 9, measuring magnetic disturbance, began climbing. Within hours, the planet shifted from calm conditions, KP 0 through 2, to active, KP 3 through 4. By 9 p.m. Universal Time on November 5th, Earth had crossed into minor storm territory, classified as G1, KP 5. That was only the prelude. By 10:53 p.m., the storm had strengthened to moderate G2 levels, KP 6. Power grid operators in high latitudes began reporting voltage fluctuations. Satellites in low orbit experienced increased atmospheric drag as the upper atmosphere expanded from energetic particle heating, increasing friction. High-frequency radio communications became unstable and unreliable. Then, at 5:36 a.m. Universal Time on November 6th, the storm reached G3, strong geomagnetic intensity. At that point, the effects were no longer abstract. They became visible to millions. The auroras, usually confined to an oval around the magnetic poles, expanded dramatically toward much lower latitudes. In North America, auroras are normally visible only in Alaska, northern Canada, and occasionally the northern border states. But during those November nights, the story was completely different. 22 U.S. states reported confirmed aurora sightings, from the expected regions of Alaska and Montana to unlikely places like Illinois, Iowa, Nebraska, even northern Kansas and Missouri. People who had never seen an aurora before found themselves staring at dancing skies of green, red, and violet, waving like celestial curtains. Residents poured out of their homes in the middle of the night, alerted by phone notifications or by excited neighbors shouting outside. They gathered in fields, parks, and beaches, gazing northward in awe. Social media erupted. Thousands of photos and videos flooded Instagram, TikTok, and YouTube. Families bundled in winter coats filmed glowing skies from suburban backyards. These weren't the usual green curtains from low-altitude oxygen emissions. This time, the skies blazed with deep crimson and magenta, the high-altitude reds produced by rarefied oxygen over 180 miles up. Brilliant purples shimmered from ionized nitrogen. Some witnesses even reported flashes of electric blue racing across the heavens, a rarer phenomenon still. For most casual observers, the auroras were simply a stunning natural show, a cosmic gift to marvel at and share online. Comment sections overflowed with amazement and gratitude. What a privilege to see this! Nature is incredible. I'll never forget this night. And from a purely aesthetic and emotional standpoint, it was indeed an extraordinary gift, the universe's own light show, rivaling any human production. Yet behind that beauty lay a more complex and unsettling reality, one that most spectators never considered. While the crowds rejoiced under glowing skies, scientists and technicians across various government agencies watched the same event from a far more anxious perspective. To them, those lights weren't just beautiful, they were visible symptoms of powerful geophysical forces testing the resilience of modern technological infrastructure. Chapter 2: The Invisible Storm and Its Consequences. The National Oceanic and Atmospheric Administration, NOAA, did not share the carefree excitement of the general public. While thousands posted selfies with shimmering auroras behind them, scientists at the Space Weather Prediction Center in Boulder issued alerts and warnings in a far more sober tone. Their technical bulletins didn't speak of celestial wonders, but of tangible threats to critical systems upon which modern civilization depends. Official reports detailed the risks with technical precision: significant voltage fluctuations in power grids, especially at high latitudes where the effects are strongest. These fluctuations can overload transformers, trigger cascading blackouts, and in severe cases, cause permanent damage to expensive equipment that may take months to replace. Satellites in low Earth orbit experience dramatic increases in atmospheric drag during G3 storms. The upper atmosphere heats and swells under the bombardment of energetic particles, expanding into altitudes where it's usually almost non-existent. The denser air creates friction against satellites, slowing them and degrading their orbits. Operators are forced to perform corrective maneuvers that consume precious propellant, shortening the operational lifespan of spacecraft that cost hundreds of millions of dollars to build and launch. High-frequency radio communications, vital for polar aviation routes, maritime navigation, and military operations, become erratic and unreliable. Pilots flying over Arctic regions lose contact with air traffic controllers for extended periods. Safety protocols then require route adjustments to more southerly paths where communication remains stable, adding flight hours, burning extra fuel, and generating massive operational costs for airlines. Global positioning systems, GPS, Galileo, and Russia's GLONASS, begin reporting positional errors greater than usual. The disturbed ionosphere refracts radio signals unpredictably, introducing variable delays that degrade accuracy. Under normal conditions, a civilian GPS receiver can pinpoint its position within 10 to 15 feet. During G3 storms, that precision can deteriorate to 60 or 100 feet, enough to cause serious problems in fields requiring pinpoint navigation, such as precision agriculture, surveying, and autonomous transport systems. These are the known and documented hazards, the officially recognized effects, studied, insured, and planned for. Insurance companies have them cataloged. Government agencies maintain contingency strategies. The space industry builds them into its engineering and operational protocols. There is a well-defined framework for understanding and mitigating these technological impacts. But that's where the conventional narrative ends and where the story becomes incomplete. Because geomagnetic storms don't just affect satellites and power grids. They can influence the Earth itself, its crust, its oceans, its atmosphere, and possibly even the biosphere living upon it. These lesser-known, less understood, and sometimes controversial effects represent a facet of space weather that deserves far more attention than it receives. When charged particles from the solar wind interact with Earth's magnetosphere and ionosphere, not all their energy is released as auroras. A significant fraction travels downward, coupling with the planet's global electrical circuit, which links the positively charged ionosphere with the negatively charged surface. This circuit forms part of what geophysicists call the global atmospheric electrical system, a phenomenon that exists constantly but intensifies dramatically during geomagnetic storms. Rapid variations in Earth's magnetic field during such storms induce electric currents in any large-scale conductor. This effect has been known since the 19th century, when early telegraph systems began experiencing mysterious disruptions coinciding with auroral displays. Telegraph operators reported their lines becoming spontaneously electrified, sometimes producing sparks and even fires. In some extreme cases, telegraphs operated without batteries, powered solely by induced currents during the most intense storms. These geoelectrical currents, also called telluric or geomagnetically induced currents, flow through the ground itself. They follow paths of least electrical resistance, conductive rock beds, saline aquifers, mineral deposits. Their magnitude depends on several factors: the storm's intensity and rate of magnetic change, the local geological conductivity, and the geometry of both natural and man-made conductive structures. In regions with favorable geology, a G3 level geomagnetic storm can induce telluric currents of hundreds of amperes flowing through the crust. These currents seek artificial conductors to complete their circuits. Metal pipelines stretching across continents, undersea telecommunication cables, and, crucially, the grounding circuits of electrical grids. When direct currents like these enter transformers designed for alternating current, they saturate the magnetic cores, causing overheating, harmonic distortion, and in severe cases, permanent failure or destruction. The March 1989 event provides a sobering case study. An extreme geomagnetic storm, rated G5, struck Earth following a series of massive solar flares. In Quebec, Canada, Hydro-Quebec's entire power grid collapsed in less than 2 minutes. Induced telluric currents saturated critical transformers, triggering cascading protection shutdowns and leaving 6 million people without electricity for 9 hours, in the middle of a freezing Canadian winter. The economic cost exceeded hundreds of millions of dollars, and some transformers suffered irreversible damage, requiring full replacement. That incident spurred major improvements in space weather monitoring and power grid protection protocols. But vulnerability remains. A 2008 NASA-commissioned study estimated that a geomagnetic storm comparable to the 1859 Carrington event, the strongest ever recorded, could cause as much as $2 trillion in damage to U.S. electrical infrastructure, potentially leaving tens of millions without power for months or even years, while specialized transformers are rebuilt and replaced. Yet telluric currents don't affect only human technology. They also interact with Earth's natural systems in ways we're only beginning to grasp. For decades, scientists have speculated about potential links between geomagnetic activity and geological processes, particularly seismic events. At first glance, the idea seems implausible. How could electromagnetic fluctuations in the ionosphere influence tectonic movements in Earth's solid crust? The energy scales appear utterly mismatched. And yet, coupling mechanisms do exist. Telluric currents flowing through the crust can alter local electric fields in fault zones. Rocks under tectonic stress exhibit piezoelectric properties. When mechanically deformed, they generate electrical charges. This direct piezoelectric effect is well documented in laboratory experiments. But there's also an inverse effect. When an external electric field is applied to stressed crystalline rock, it can produce additional microscopic deformations. Could geomagnetically induced telluric currents flowing through fault zones already under tectonic stress provide that final nudge triggering a seismic rupture? Most mainstream seismologists have historically dismissed this idea as implausible. Earthquakes, they argue, are driven by massive tectonic forces, accumulating over decades or centuries. The energy released in a large quake is astronomical, equivalent to multiple nuclear detonations. How could a comparatively weak electromagnetic disturbance trigger such a release? The answer may lie in the concept of critically loaded systems. A tectonic fault, accumulating stress over years, gradually approaches a critical state, a threshold of instability where only a small perturbation is needed to unleash catastrophic slippage. It's like an avalanche. A mountainside may collect snow for weeks, inching toward its critical angle of stability. Eventually, the slightest disturbance, perhaps a skier's movement or even a loud shout, can trigger the entire slope to collapse. The energy comes from the accumulated snow, not the trigger itself, but without that trigger, the avalanche might not occur at that moment. Similarly, if a fault is already near its breaking point, an additional perturbation of any kind could provide the final push. Geomagnetically induced telluric currents represent a time-varying disturbance that intensifies during storms and then subsides. If such a fluctuation coincides with a fault in a critical state, it could influence the precise timing of an earthquake. Several peer-reviewed studies have examined statistical correlations between geomagnetic activity and seismicity. Results remain mixed and controversial. Some find significant positive correlations, particularly for shallow quakes in tectonically active regions. Others find none, or correlations so weak they may be coincidental. The seismological community remains divided. Most remain skeptical, while a small but persistent minority argues the effect is real but subtle. Part of the challenge lies in the complexity of the statistics. Earthquakes follow power law distributions. Many small ones, few large ones. Geomagnetic storms are relatively rare, especially strong ones. Demonstrating statistically significant correlations requires vast datasets and sophisticated analysis to account for multiple confounding variables. The noise is high. The signals are faint. Beyond the scientific debate, there's another underexplored dimension of geomagnetic impact: its biological effects. The idea that geomagnetic storms could influence living organisms, including humans, is met with skepticism in mainstream Western medicine. Yet, a substantial body of research, primarily from Russian and Eastern European scientists, suggests such effects are real and measurable. Epidemic disruptions in sleep patterns, changes in blood pressure, and altered heart rate variability. Some researchers propose that Earth's magnetic field and its fluctuations may influence biological rhythms, nervous systems, and cardiovascular processes through mechanisms involving magnetoreception, interactions with the pineal gland, and effects on free radical chemistry within cells. The Western medical community has been slow to accept these findings, partly due to inconsistencies across studies, partly for lack of clearly established biophysical mechanisms, and partly due to cultural biases about what environmental influences seem plausible. Yet the sheer volume of data suggests that something is indeed happening, even if we don't yet understand how. So what truly occurred during those early November days of 2025? We know for certain that intense G3 geomagnetic storms struck Earth. We know millions witnessed spectacular auroras. We know technological systems suffered documented disturbances. But were there other effects? Did powerful telluric currents surge through the crust? Did tectonic fault zones experience added electromagnetic stress? Did living organisms, from microbes to humans, undergo subtle biological shifts? The honest answer is that we don't know for sure. Space weather science focuses primarily on technological effects because they are measurable, economically significant, and clearly attributable. Geological and biological effects, if they exist, are far subtler, harder to detect, and more controversial to claim. Yet the absence of certainty is not the same as the absence of effect. And here arises an unsettling question. If the solar storms of early November 2025 exerted influences beyond what official science recognizes, and if those influences coincided with other phenomena unfolding elsewhere in the solar system, phenomena only just coming into focus, then perhaps we should pay far closer attention to timing, to coincidences, to patterns that emerge when we examine multiple kinds of events together. Because while Earth was being struck by geomagnetic storms, while auroras danced far south of their usual boundaries, while telluric currents flowed invisibly beneath our feet, something else was happening deep within the solar system. Something astronomers were about to discover, a discovery that would change everything. Chapter 3: The Discovery That Changed Everything. On October 29, 2025, just days before the Sun unleashed its electromagnetic fury, a team of astronomers operating telescopes at the Mauna Kea Observatory in Hawaii detected something unusual. It wasn't extraordinary in itself. Modern telescopes discover new objects all the time. Asteroids, comets, trans-Neptunian bodies. Most turn out to be routine residents of the solar system, following predictable orbits. But this object was different. The first observations showed a faint point of light moving against the background of fixed stars. Its motion immediately caught the attention of orbital dynamics specialists. It didn't follow a typical elliptical orbit bound by the Sun's gravity. Its path was hyperbolic, an open curve indicating excessive velocity, an escape trajectory. This object wasn't orbiting the Sun. It was visiting briefly, before hurtling back into interstellar space. Preliminary orbital calculations confirmed what astronomers were beginning to suspect with growing excitement. It was an interstellar object, only the third confirmed visitor from beyond our solar system. The first had been 1I Oumuamua, discovered in October 2017, an elongated, tumbling body that baffled scientists with its unexplained non-gravitational acceleration. The second was 2I Borisov, detected in August 2019, a clearly active comet behaving more conventionally. Now came the third, officially designated 3I Atlas. The name came from the Atlas telescope system, the Asteroid Terrestrial Impact Last Alert System, a network designed to detect potentially hazardous asteroids. Although 3I Atlas posed no impact threat, its trajectory would bring it relatively close to Earth in astronomical terms, offering an unprecedented opportunity for detailed study. In the days following the discovery, telescopes worldwide turned their instruments toward the newcomer. Observations multiplied rapidly. Spectroscopy to analyze its surface composition, photometry to measure brightness and variability, high-precision astrometry to refine its orbit. Each new data point added to the emerging portrait of 3I Atlas. Its size was estimated using photometric and thermal modeling. Assuming a reasonable albedo, a surface reflectivity comparable to that of other small solar system bodies, astronomers calculated a diameter between 800 and 1200 meters. Not massive by astronomical standards, but far from tiny. Comparable to well-studied near-Earth asteroids, it was large enough that gravity could compress it into an approximately spherical shape if its composition allowed. Spectroscopic measurements revealed an unusually dark surface. Its albedo was low, reflecting only 4 to 6% of the sunlight it received. That placed it among the darkest known objects in the solar system, similar to primitive carbonaceous asteroids or cometary nuclei coated in radiation-processed organic compounds. Yet unlike active comets, 3I Atlas showed no visible coma or tail, even under sensitive telescopic observation. Its speed was remarkable. At perihelion, the point of closest approach to the Sun, 3I Atlas was traveling about 32 kilometers per second relative to the Sun. For context, Earth orbits at roughly 30 kilometers per second, and highly eccentric comets can reach 50 or 60. But what made 3I Atlas notable wasn't its absolute speed near the Sun. It was its excess velocity beyond the local escape speed. Every point in the solar system has a specific escape velocity, the minimum speed needed to break free from the Sun's gravity. Near the Sun, that threshold is high. Farther away, it's lower. An interstellar object entering the solar system accelerates as it falls toward the Sun, reaching maximum speed at perihelion. Then, as it moves outward again, it slows, but if its trajectory is hyperbolic, meaning it exceeds the escape velocity, it will decelerate yet never stop, eventually leaving the solar system with residual velocity intact. Calculations showed 3I Atlas had an orbital eccentricity of about 1.4, firmly hyperbolic. Its velocity at infinity, the speed it would retain once solar gravity no longer affected it, was estimated at 8 kilometers per second. In other words, 3I Atlas entered the solar system traveling at that speed, accelerated toward the Sun, swung around at 32 kilometers per second, and was now departing, gradually slowing until it recovered its original 8 kilometers per second in deep space. 8 kilometers per second is impressive for an interstellar traveler. It's higher than the relative velocities typical of nearby stars, which orbit the galactic center at around 220 kilometers per second, but usually differ from the Sun by only a few kilometers per second. An object ejected from another star's planetary system would normally share that star's galactic motion, meaning only minor relative differences, perhaps 1 to 3 kilometers per second, when it encountered our solar system. 3I Atlas, however, was moving much faster. Its velocity suggested one of two possibilities. Either it had been dramatically accelerated during its ejection, perhaps by a close encounter with a giant planet acting as a gravitational slingshot, or it originated in a region of the galaxy with different kinematic conditions, perhaps a young stellar cluster where relative stellar velocities are higher. Its incoming direction was equally intriguing. Its velocity vector pointed toward the constellation Lyra, near the bright star Vega. That didn't necessarily mean it came from Vega. Vega lies just 25 light-years away, but at 8 kilometers per second, 3I Atlas would have taken hundreds of thousands of years to cover that distance. During that time, both Vega and the Sun would have shifted significantly in their galactic orbits. Tracing the object's path backward through galactic space, accounting for stellar motions, was a complex task requiring precise velocity data and detailed galactic dynamics modeling. Some astronomers began doing just that, using stellar catalogs like Gaia, which provides ultra-precise measurements of billions of stars' positions and motions. Preliminary analyses failed to identify any obvious stellar source. I-Atlas might have been expelled from a planetary system millions of years ago, wandering through interstellar space until its chance encounter with ours. Or perhaps it had a more exotic origin altogether. As astronomers refined its orbit and studied its physical properties, subtle anomalies began to appear. Small deviations from expectations that, while individually explainable, together hinted at something more intriguing. The first anomaly concerned its brightness. 3I Atlas displayed periodic variations, as expected from a rotating body. Most small objects rotate, and if irregular in shape or surface reflectivity, their brightness fluctuates as they turn. The rotation period of 3I Atlas was measured at roughly 7.3 hours, typical for its size. Yet the amplitude of those variations was unexpectedly small, only about 10% from peak to trough. For an irregular object, one would expect much larger swings, often 50% or more. This suggested either that 3I Atlas was unusually spherical, or that its surface had remarkably uniform reflectivity. Both options were statistically unlikely, though not impossible. The second anomaly came from high-precision astrometry. When astronomers compared observed positions with those predicted by purely gravitational models, they found tiny discrepancies. The object wasn't exactly where Newtonian physics said it should be. The offsets were minuscule, just a few milliarcseconds, equivalent to millionths of a degree, but consistent and systematic. This type of deviation had been observed before with 1I/Oumuamua. In that case, the anomaly was attributed to non-gravitational acceleration, an extra push beyond solar gravity. For comets, such accelerations are common and well understood, caused by jets of sublimating gas acting like a rocket thrust. But Oumuamua showed no visible activity, no coma, no tail, making its acceleration mysterious and controversial. Proposed explanations ranged from invisible outgassing of hydrogen or nitrogen ice to the release of trapped organic molecules, or even solar radiation pressure acting on an exceptionally thin, lightweight structure, a natural solar sail. The most speculative idea, advanced by Harvard astrophysicist Avi Loeb, suggested that Oumuamua might be an artificial object, a technological solar sail of extraterrestrial origin. The hypothesis sparked heated debate and was widely dismissed by the astronomical community as highly improbable and lacking supporting evidence. Now, with 3I Atlas showing similar orbital deviations but no visible cometary activity, the situation became intriguing once again. Was the same mechanism at work, or was this something else entirely? Astronomers debated intensely. Most leaned toward natural explanations: invisible outgassing, non-principal rotation producing torque, systematic measurement errors. Yet a minority began to consider less conventional possibilities. The third anomaly was perhaps the most subtle and potentially the most consequential: timing. 3I Atlas reached perihelion, its closest point to the Sun, on November 15, 2025. Its closest approach to Earth would occur around December 20, passing at about 0.08 astronomical units, roughly 12 million kilometers. Cosmically speaking, that is astonishingly near, far closer than any previous confirmed interstellar encounter. What made this timing remarkable was the broader context. The discovery of 3I Atlas on October 29th had been followed almost immediately by the powerful solar storms of early November. Its perihelion coincided with the Sun's peak activity of that cycle. Its close approach to Earth in December would align with events that had not yet occurred, but which some were beginning to predict based on emerging patterns. And here, the story took a fascinating and deeply unsettling turn. Because 3I Atlas wasn't alone, there was something else out there, something astronomers were about to discover, something whose connection to 3I Atlas would raise questions that challenged everything we thought we understood about the cosmos and our place within it. The days following the discovery were frantic within the astronomical community. Observation proposals flooded telescope time allocation committees. Everyone wanted to study the visitor before it drifted too far and faded from view. The world's largest optical telescopes, the Very Large Telescope in Chile, the Keck and Gemini observatories, and the space-based Hubble and James Webb telescopes, all devoted precious hours to 3I Atlas. Radio telescopes joined in as well. Arecibo had collapsed in 2020, but other instruments, the Green Bank Telescope in West Virginia and the Australian Square Kilometre Array Pathfinder, turned their antennas toward 3I Atlas, searching for any radio emission that might indicate, what exactly? Natural asteroids don't emit radio waves. Comets sometimes do, but 3I Atlas showed no coma. So why search? Because some astronomers, quietly, without fanfare, were entertaining the possibility that 3I Atlas might not be entirely natural. Avi Loeb's earlier proposal about Oumuamua, controversial as it was, had planted a seed. If extraterrestrial civilizations exist and are technologically advanced, why wouldn't they send probes to explore the galaxy? Such probes could drift between stars, occasionally crossing planetary systems like ours. From a distance, they'd appear identical to natural interstellar objects, unless they were transmitting or exhibited unmistakably artificial traits. The radio searches found nothing artificial. No transmissions, no coherent signals, nothing suggesting active technology. This surprised few. An interstellar probe designed for observation would likely operate in passive mode, listening rather than broadcasting. Transmitting would consume energy and expose its presence, something a reconnaissance mission would avoid. But then came the second discovery, and everything became exponentially more complicated. Chapter 4: The Mysterious Companion. On November 10, 2025, barely 2 weeks after the initial discovery of 3I Atlas, and in the midst of the geomagnetic storms shaking Earth, an amateur astronomer in New Zealand made an extraordinary find. Using a 16-inch telescope equipped with a sensitive CCD camera, he was performing a routine follow-up on 3I Atlas when he noticed another faint object in the same field of view. At first, he assumed it was a background asteroid or a data artifact, but after carefully processing the images, subtracting the stars and tracing the object's motion across multiple exposures, he realized the second object was moving in a similar way to 3I Atlas. Not identical, but close enough to suggest a dynamic connection. He reported his observations to the electronic circulars of the Minor Planet Center, the international body that coordinates the tracking of small solar system objects. Within hours, other astronomers confirmed it. There was indeed a second object, far dimmer than 3I Atlas, traveling along a roughly parallel but distinct trajectory. Preliminary orbital calculations revealed something astonishing. The second object also followed a hyperbolic path. It too was an interstellar visitor. Its velocity vector at infinity was similar but not identical to that of 3I Atlas, differing by a few kilometers per second and a few degrees in direction. It received the provisional designation C/2025 V1, the C initially indicating it might be a comet, though later observations would show no cometary activity. The odds that two unrelated interstellar objects would pass through the inner solar system simultaneously by pure coincidence were astronomically small. Interstellar visitors are exceedingly rare. Based on the discoveries of Oumuamua and Borisov, astronomers had estimated that perhaps 1 or 2 such objects might pass through the inner system per decade, and now 2 at once? The conclusion seemed inescapable. The two must be related. But how? Several hypotheses emerged. The first proposed that C/2025 V1 was a fragment of 3I Atlas, split off sometime during its long interstellar journey, or perhaps near perihelion under solar stress. Comets sometimes fragment under tidal forces or thermal strain. If 3I Atlas had fractured, a piece could have drifted away at low relative speed, producing two bodies on similar but slightly divergent orbits. Yet the details didn't fit. The orbital differences suggested that if they had once been joined, their separation had occurred long ago, likely years before entering the solar system. Moreover, the relative velocities required to explain the observed divergence were far too large for ordinary fragmentation. It would have taken several kilometers per second, more like an explosion than a gentle break. The second hypothesis suggested both objects originated in the same stellar system and were ejected together or in quick succession, perhaps during a chaotic planetary system upheaval that expelled multiple bodies at once. That scenario was more plausible. In a young planetary system experiencing dynamic instability, several objects could be cast out along similar paths, traveling loosely together through interstellar space for millions of years before encountering another star system. But detailed trajectory analysis revealed something peculiar. The orbits of 3I Atlas and C/2025 V1 weren't merely similar. They were correlated in a way that implied coordination, not coincidence. When astronomers computed their relative positions over time, they found that C/2025 V1 appeared to be following 3I Atlas, maintaining roughly the same distance behind it along its track. The separation was about 9 million miles, around 0.1 astronomical units, roughly 1/3 the Earth-Moon distance multiplied by 100. What baffled scientists was that the distance remained nearly constant as both objects traversed the solar system. If they were merely fragments, The gap should have widened steadily as their slightly different speeds diverged. It didn't. The distance held steady. That led to a third, far more unsettling hypothesis. C-2025 V1 wasn't an accidental fragment, but a deliberate companion, an independent object traveling in coordinated formation with the first. If true, this meant they weren't passive natural bodies drifting under gravity's pull, but actively controlled technological craft. The astronomical community reacted with a mix of excitement, skepticism, and disbelief. Most scientists remained cautious, insisting on more data before embracing extraordinary conclusions. Natural explanations, however unlikely, weren't yet ruled out. Perhaps an unrecognized orbital resonance or subtle planetary influence was maintaining their spacing. But as further data arrived, natural explanations became harder to sustain. High-precision astrometric measurements showed that both 3I Atlas and C-2025 V1 exhibited slight non-gravitational accelerations. Each was deviating gently from the purely Newtonian paths predicted by solar and planetary gravity, and, crucially, those deviations were correlated, as though both objects were performing synchronized trajectory adjustments to preserve formation. C-2025 V1 was estimated to be 1,000 to 1,300 feet across, much smaller than 3I Atlas. It was vastly dimmer, detectable only with large telescopes, which explained why it hadn't been spotted earlier. It displayed no visible cometary activity, no coma, no tail, just like its counterpart. Some astronomers began informally calling C-2225 V1 the escort, or the satellite, of 3I Atlas, though those terms implied a relationship not yet proven. Others preferred neutral labels like the companion object, but the implication was clear. The two were meaningfully connected. Speculation multiplied. If 3I Atlas were an interstellar craft, what role did C-2025 V1 serve? Was it a smaller reconnaissance module released from a mothership? A communications relay? A scientific probe operating from an alternate vantage point? Or something beyond human imagination, performing a function we couldn't yet comprehend? Harvard astrophysicist Avi Loeb, once mocked for proposing that Oumuamua might be artificial, now found a more receptive audience. In interviews and essays, he argued that the presence of two interstellar objects flying in coordinated formation fit precisely what one would expect from an extraterrestrial exploration mission, not from random natural debris. Human missions often deploy multiple cooperating spacecraft, orbiters and landers, motherships and drones, telescopes and relay satellites. Why wouldn't another civilization do the same? If we were to send an interstellar expedition, Loeb noted, we wouldn't send a single craft. We'd deploy multiple components with specialized roles to maximize data collection. What we're seeing with 3I Atlas and C-2025 V1 matches exactly that kind of mission architecture. Skeptics countered that the lack of radio signals, absence of visible structural features in images, and the failure to observe any overtly artificial behavior, such as sharp maneuvers or energy emissions, meant the extraterrestrial hypothesis lacked direct evidence. The orbital correlations, intriguing as they were, could still have natural explanations not yet understood. Then came the high-resolution spectroscopic data, and the mystery deepened. Astronomers using powerful spectrographs on large telescopes analyzed the reflected light from both objects in extraordinary detail. Spectroscopy is one of astronomy's most revealing tools, allowing scientists to determine the chemical composition of distant bodies by examining which wavelengths of light they absorb or reflect. Different minerals and compounds leave unique spectral fingerprints. The spectra of 3I Atlas and C-2025 V1 were perplexing. They showed absorption features consistent with complex organic compounds, similar to those found in primitive, carbon-rich asteroids and cometary nuclei. That was normal enough, but they also exhibited unusual near-infrared features that matched no known mineral or compound. Some spectroscopists suggested the anomalies arose from minerals altered by cosmic radiation during millions of years in interstellar space. Others proposed exotic organics not present in our solar system, and a small minority raised the possibility that the signatures were consistent with engineered materials, specifically composites or alloys designed with deliberate optical properties. That last idea was highly speculative and met with deep skepticism. Yet the fact that it was being discussed in peer-reviewed journals signaled how far the debate had evolved. The hypothesis of artificial origin for 3I Atlas and C2025 V1 was no longer dismissed outright as pseudoscience. It was being examined as a legitimate possibility worthy of rigorous investigation. While astronomers debated spectral interpretations, another group of researchers was looking elsewhere, analyzing temporal correlations between the early November solar storms, the arrival of 3I Atlas and C2025 V1, and a string of other phenomena just beginning to emerge, because it turned out that geomagnetic storms weren't the only unusual events unfolding at that time. Earth itself had started to tremble, several notable earthquakes striking across the globe, their timing eerily close to the peaks of geomagnetic activity. Chapter 5: Unsettling Seismic Patterns. For decades, the supposed link between solar activity and earthquakes had been one of the most controversial and marginalized topics in earth sciences. Most seismologists dismissed it outright as spurious correlation, pseudoscience, or mystical thinking. Earthquakes, they insisted, were driven solely by tectonic processes, the slow movement of lithospheric plates, the buildup of elastic strain along faults, and the sudden release of accumulated energy. The forces involved were immense, the product of mantle convection and planetary-scale gravitational dynamics. How could something as fleeting as an electromagnetic storm in the upper atmosphere influence processes occurring miles beneath the surface? Yet a persistent minority of researchers had continued to explore the connection, compiling statistical data suggesting that something was happening, even if the mechanisms remained unclear. Studies published in geophysical journals showed weak but statistically significant correlations between geomagnetic activity indices and earthquake frequency, especially for shallow quakes in tectonically active regions. Proposed mechanisms varied. Some researchers emphasized geomagnetically induced telluric currents, arguing these could alter stress conditions in fault zones through piezoelectric effects. Others pointed to shifts in atmospheric pressure and electrical charge during geomagnetic storms, suggesting that even tiny additional forces could be enough to disturb tectonic systems already near failure. A few proposed more exotic influences, minute changes in Earth's rotational length of day caused by magnetospheric interactions, or subtle fluctuations in the gravitational field. Mainstream seismology remained skeptical, largely because the observed correlations were weak, inconsistent across studies, and lacked a convincing physical mechanism. The principle of seismic triggering was widely accepted. A fault heavily loaded with stress could be nudged into rupture by small perturbations, such as changes in pore pressure from heavy rainfall, the filling or draining of large reservoirs, or even tidal stresses from the moon and sun. But extending this principle to geomagnetic storms required proving that such storms produced measurable physical disturbances comparable in magnitude to known triggers. That's where the events of early November 2025 became crucial, because they provided what previous studies lacked: a clear, well-documented case with precise temporal overlap between intense geomagnetic storms and subsequent seismic activity. On November 7, 2025, the same day the first coronal mass ejection struck Earth's magnetosphere and triggered a G3 geomagnetic storm, a magnitude 6.2 earthquake hit the Kamchatka Peninsula in Russia's far east. Kamchatka is highly active tectonically, part of the Pacific Ring of Fire, and earthquakes there are routine. A 6.2 event is serious but not unusual. What was remarkable wasn't the quake itself, but its timing. It struck roughly 14 hours after the CME impact, just as the geomagnetic storm peaked, with KP values rising to 6 and 7. Magnetometer stations across Kamchatka recorded extreme fluctuations in Earth's magnetic field during the hours preceding the quake. 2 days later, on November 9, a magnitude 5.8 quake rattled Sichuan province in China, another seismically active region, but one with a completely different tectonic setting. That event occurred as the second CME hit Earth, sparking another round of intense geomagnetic disturbance. 2 significant earthquakes in 3 days, each coinciding with peaks in geomagnetic activity. Taken separately, each could be dismissed as coincidence. Both regions quake frequently, but together, their timing was statistically unlikely to be random. Seismologists began re-examining historical earthquake catalogs with renewed interest, searching for similar patterns during past geomagnetic storms. Some retrospective analyses revealed intriguing alignments. During the powerful March 1989 geomagnetic storm, the one that caused the Quebec blackout, there had also been a noticeable uptick in moderate quakes worldwide. The Halloween storms of October 2003, among the strongest of solar cycle 23, showed a similar pattern. But correlation isn't causation, skeptics reminded everyone. With enough data and hindsight, it's always possible to find patterns that arise purely by chance. The real test of any scientific hypothesis lies in prediction. Can future earthquakes be forecast based on geomagnetic activity? And here the story took an extraordinary turn, because some researchers tried exactly that. Their model didn't attempt to predict specific quakes with precise location or magnitude that remains beyond current science, but to identify temporal risk windows, periods when geomagnetic conditions might act as triggers for faults already near critical stress. Using the early November storms and continued solar activity forecasts, the team calculated elevated risk windows spanning late November through early December 2025. They didn't publish their findings widely, sharing them only with government seismic monitoring agencies in several countries, and with explicit warnings. The research was experimental and speculative, not to be interpreted as a forecast of imminent earthquakes. The scientists involved were both hopeful and fearful. Hopeful that their model might be validated spectacularly, and fearful of what that validation would imply. If the connection were real and quantifiable, it would mean decades of seismological understanding were incomplete, that a key triggering mechanism had been overlooked. The deeper question was what to do with that knowledge if proven true. Should public warnings be issued during geomagnetic storms? Could lives be saved with early alerts, or would such warnings instead provoke panic, costly evacuations, and public fatigue when most risk windows produced no major quakes? Earthquakes are inherently stochastic. Even if geomagnetic storms raise the probability of quakes on critically stressed faults, most storms wouldn't trigger events, simply because most faults at any moment aren't close enough to rupture. Any predictive model would have high false positive rates, many alerts without results, and also false negatives, quakes occurring outside predicted windows, driven purely by tectonics. While these ethical and scientific debates unfolded quietly within agencies and academic committees, the general public remained unaware. The early November quakes were reported by the media as ordinary events in active seismic zones. Some news pieces mentioned recent solar storms, but drew no causal link. The scientists involved stayed cautious, knowing premature claims could destroy their credibility if the correlations proved illusory. But within specialized circles, discussion intensified. Scientific conferences scheduled for December and January hastily added sessions on solar-terrestrial coupling and geomagnetic-induced seismicity. Research proposals, once dismissed as fringe, began receiving funding. The paradigm was shifting. Then, someone posed the obvious, unsettling question. What were the odds that the most intense solar storms in months, the arrival of two possibly artificial interstellar objects, and a cluster of temporally correlated earthquakes all happened at once? By chance? To estimate that, one had to combine the independent frequencies of each phenomenon. G3-level geomagnetic storms occur a few times per year near solar maximum. Interstellar objects, based on past detections, enter the inner solar system perhaps once every few years. The odds of two appearing simultaneously are extraordinarily small, maybe once in centuries or millennia. Temporally correlated earthquake clusters, if real, occur perhaps a few times per solar cycle. Multiply those probabilities together, and you get an astronomically tiny number. The likelihood of all these events coinciding purely by chance was effectively zero. That left two possibilities. Either humanity was witnessing a statistical fluke so improbable it strained belief, or these phenomena were causally connected. And if they were connected, how? The obvious yet nearly unthinkable answer was that 3I Atlas and C2025 V1 weren't passive travelers merely passing through. They were active participants, observing, studying, and perhaps even influencing the unfolding events. Their arrival during solar maximum was not coincidence, it was intentional. Their positioning for optimal observation of Earth during geomagnetic storms and subsequent seismic activity suggested a mission of scientific investigation with specific objectives. But what exactly were they studying, and why? If the predictive model proved correct, if quakes did occur during the forecasted late November and early December windows, the evidence for a real connection between geomagnetic activity and seismicity would grow much stronger. And the question of whether 3I Atlas was merely observing or actively participating would become far more urgent. Late November approached. The scientific world waited, half eager, half afraid. The risk windows would open around November 20th and extend into early December. Would significant earthquakes occur, or would the model fail, exposing the early November correlations as coincidences? Time would tell. Meanwhile, 3I Atlas and its silent companion C2025 V1 continued their steady passage through the inner solar system, aligning themselves, it seemed, for their main objective, the detailed observation of Earth during the peak of solar and geomagnetic activity expected to last through year's end. Seismic monitoring agencies in tectonically active regions had been discreetly briefed on the forecast windows. They heightened vigilance, ensured emergency teams were ready, and reviewed communication protocols in case significant events occurred. Yet no public alerts were issued. No one wanted to spark unnecessary alarm over an untested model. It was an unprecedented situation. For the first time, scientists were attempting to use solar and geomagnetic data to anticipate periods of heightened seismic risk. The coming weeks would determine whether this radical idea held promise or was merely another futile search for patterns in random noise. Beneath that scientific uncertainty, however, lay a deeper, far more disturbing question. If the predictions came true, if earthquakes struck exactly when the model said they would that prove a natural correlation or extraterrestrial experimentation? Were we discovering a new geophysical phenomenon or unwitting subjects in a cosmic research project? The distinction mattered profoundly. If natural, it would represent a breakthrough that could one day save countless lives through improved early warning systems. If artificial, it would raise existential and ethical dilemmas humanity was utterly unprepared to face. November drew to a close. December loomed ahead, and with it came answers, or perhaps only more questions that would reshape our understanding of the cosmos and of ourselves. Chapter 6: The Scientific Mission Hypothesis. If we accept, even tentatively, that 3I Atlas and C-2025 V1 are technological artifacts of extraterrestrial origin, then the next question is obvious. What is their purpose? Why travel light years through interstellar space to visit our solar system now, during this precise period of heightened solar activity? The simplest answer, the one requiring the fewest extraordinary assumptions, is that they are part of a scientific exploration mission, not an invasion, not colonization, nor even deliberate first contact with humanity, but systematic observation and data collection on a stellar system and its planets. Exactly what we would do, given the means. In fact, we've already planned such missions ourselves. The Breakthrough Starshot Project, a privately funded initiative announced in 2016, proposed sending fleets of nanoscale spacecraft propelled by laser-driven light sails toward Alpha Centauri, 4.3 light-years away. These tiny probes, traveling at 20% of the speed of light, would reach their destination in roughly 20 years, transmitting images and data back to Earth. The technical hurdles are enormous and may never be fully overcome, but the concept itself is scientifically sound. If we, with our fledgling 21st century technology, are already designing interstellar probes, what would a civilization thousands or millions of years ahead be capable of? Presumably, they would have perfected interstellar exploration long ago, operating vast networks of automated probes, surveying sectors of the galaxy, and gathering data from thousands of star systems. Our galaxy contains between 200 and 400 billion stars, most of which are now known to host planets. If even a small fraction of those systems produced technologically advanced civilizations capable of exploration, the galaxy could be teeming with silent, robotic explorers, most of them unnoticed unless they passed unusually close to us or chose to reveal themselves. So, assume 3I Atlas is such a probe. What would it study here, specifically? The timing provides a major clue. Its arrival during solar maximum would hardly be accidental. The roughly 11-year solar cycle is a defining characteristic of our Sun, detectable from interstellar distances through variations in luminosity and radio emissions. A civilization planning an observational mission to our solar system might deliberately time its arrival to coincide with solar maximum, when the Sun's most dramatic and revealing phenomena occur: flares, coronal mass ejections, and powerful geomagnetic storms. Why study a solar maximum? Because it reveals crucial data about star-planet interactions. How a planet responds to stellar outbursts depends on its magnetic field, atmosphere, geology, and biosphere, if it has one. Earth, with its robust magnetosphere, dense atmosphere, and living ecosystem, responds very differently from Mars, with its weak magnetic field, or Venus, whose thick atmosphere lacks magnetic shielding. By observing multiple planets simultaneously during solar maximum, a probe could perform a kind of controlled experiment. one uniform stimulus, solar activity, applied to several diverse subjects, planets, to infer the internal structures, atmospheric, dynamics, and potential biosignatures of each. Earth would be uniquely interesting, being the only known planet with complex life and a technological civilization. How does an active biosphere respond to geomagnetic stress? How does a technological species cope when its electromagnetic infrastructure is disrupted by space weather? These are questions of profound scientific value to any advanced observer. The presence of C/2025V1 traveling in coordinated formation implies a sophisticated mission architecture. Human missions often use multiple components: orbiters and landers for Mars, motherships and impactors for asteroids. By analogy, 3I Atlas, the larger body, roughly a kilometer wide, could serve as the main craft, housing propulsion, data storage, and primary instruments, possibly even artificial intelligence, or, hypothetically, crew. The smaller C/2025V1, around 300 to 400 meters across, could be a secondary module, specialized for complementary observations or functioning as a communications relay. Their separation, about 15 million kilometers, roughly 0.1 astronomical units, is ideal for stereoscopic observation of the inner solar system, far enough for meaningful triangulation, yet close enough for direct communication. If the mission's purpose is to study Sun-Earth interactions, this positioning during solar maximum is perfect. They can monitor the Sun up close while simultaneously observing Earth's magnetospheric and atmospheric reactions. It's a natural laboratory for plasma physics, magnetospheric dynamics, and solar-terrestrial coupling. But the situation becomes more intriguing when considering seismic correlations. If earthquakes are indeed temporally linked to geomagnetic storms, via induced telluric currents or piezoelectric stress in crustal rocks, then the Sun-Earth seismic coupling becomes a rare and scientifically rich phenomenon worth studying. From an extraterrestrial perspective, Earth would be a goldmine of data, a tectonically active planet with moving plates, volcanism, and frequent quakes, protected by a strong magnetic field and bathed in a variable stellar wind. When the star erupts, the planet's magnetic field channels electric currents through its crust, possibly influencing the precise timing of fault ruptures. Such complexity would be rare and scientifically irresistible. If 3I Atlas and its companion are studying this very relationship, their timing makes perfect sense. Arrive during solar maximum, monitor both solar outbursts and planetary responses, record seismic, magnetic, and atmospheric coupling effects. Could they detect earthquakes from space? Yes, in several ways. Large quakes generate planetary oscillations, causing Earth to ring like a bell in extremely low frequencies, detectable as gravitational or inertial fluctuations. They also create ionospheric disturbances, measurable as shifts in total electron content and electromagnetic emissions from crustal deformation or piezoelectric discharges. A probe equipped with precision instruments could easily monitor such signatures remotely. Thus emerges a coherent narrative. 3I Atlas is an extraterrestrial scientific probe arriving intentionally during solar cycle 25's maximum. Its mission? To study the interplay between solar activity, geomagnetic storms, and terrestrial processes, possibly including earthquakes. C/2025V1 serves as its companion module, providing complementary vantage points or communication links. Their synchronization with November's solar storms was no coincidence. It was scheduling. They may even possess predictive capability for stellar cycles based on long-term monitoring from deep space. The seismic correlations observed in November and those predicted for December need not be caused directly by the probes. They could simply be natural phenomena that the visitors came to document. Earthquakes occur from tectonic forces, geomagnetic storms from solar physics, but their coupling, if real, would be of enormous scientific interest to anyone studying geophysical systems across the galaxy. This interpretation is appealing because it's parsimonious, no sinister motives, no physics-breaking technologies, just observation. It requires only 3 assumptions. Advanced extraterrestrial civilizations exist. Some conduct interstellar exploration. Our system is scientifically interesting enough to merit study. All 3 are plausible under current scientific understanding. Life elsewhere is statistically likely. Interstellar travel, while challenging, violates no physical law, and a habitable planet with intelligent life would be an irresistible target. Still, even this benign hypothesis leaves troubling gaps. If 3I Atlas were merely observing, why are the timing correlations so exact? How could earthquakes occur so precisely within predicted windows? Could our primitive geomagnetic seismic models truly be that accurate? Or is there another factor at play? And what if 3I Atlas is not a passive observer? What if it possesses the capability to influence the phenomena it studies? Chapter 7. The Unsettling Possibility. There's a question most scientists avoid voicing aloud, one that surfaces only in private during quiet, sleepless hours. A question that challenges not only our understanding of physics, but the very foundations of our assumptions about humanity's place in the cosmos, and our vulnerability to forces beyond imagination. That question is this: what if 3I Atlas isn't just observing solar activity and its effects on Earth, but actually influencing them? At first glance, the idea seems absurd. The Sun is a colossal sphere of plasma, with a mass of 2 × 10⁻³ kilograms, 333,000 times that of Earth. Its core burns at 27 million degrees Fahrenheit, fusing 600 million tons of hydrogen into helium every second, releasing energy equal to 1 billion hydrogen bombs. Solar flares and coronal mass ejections involve magnetic reconnection events releasing 10^5 joules or more within minutes. How could an artificial object a mile across, no matter how advanced, affect processes on such a titanic scale? The disparity in energy seems insurmountable. It's like suggesting an ant could steer Earth's weather, or a grain of sand could redirect a hurricane. Physics appears to rule it out completely. But what does impossible truly mean when applied to technology millions of years ahead of ours? Just 2 centuries ago, the notion of splitting atoms and releasing enough energy to vaporize cities would have been unthinkable. A century ago, bouncing radio waves off the moon was science fiction. Half a century ago, global internet and pocket-sized supercomputers were fantasy. Each generation projects its limitations forward and calls them permanent. Yet human history is one long record of overcoming the impossible. And our technological civilization is still in its infancy, barely a few centuries old. What could a civilization accomplish after 1 million years of continuous advancement? Physicist Michio Kaku proposed a now famous scale of civilizations based on energy mastery. A Type 1 civilization harnesses all the energy of its planet, about 10⁻16 watts for Earth. A Type 2 civilization controls the energy of its star, roughly 10^6 watts for a Sun-like star, perhaps via Dyson structures surrounding it. A Type 3 civilization commands the energy of an entire galaxy, around 10^6 watts. Humanity today sits around Type 0.7, using about 10^13 watts, far below our planet's full potential. At our current rate, we might reach Type 1 in a few centuries, and Type 2 in several millennia. A civilization capable of interstellar travel would almost certainly be at least Type 2, possibly advancing toward Type 3, possessing power resources that to us would appear indistinguishable from magic. Could such a civilization influence a star's activity? Theoretically, yes, if it understood stellar plasma dynamics deeply enough. It wouldn't need to match the energy of a flare, only to trigger one already on the verge of instability. The analogy mirrors seismic triggering on Earth. You don't supply the energy of an earthquake. You apply a precisely timed nudge to a fault already near rupture. The energy comes from accumulated tectonic stress, not the trigger. Likewise, solar flares arise when twisted magnetic fields in the sun's corona reach a critical threshold. A small, well-placed perturbation could cause a massive release. Could an advanced technology provide that nudge? In principle, yes. Inject charged plasma or particle beams into the unstable coronal region. Use powerful electromagnetic fields to distort magnetic loops. Fire intense lasers to heat local plasma and alter pressure dynamics. None of these require matching the flare's total energy, only pushing the system past its tipping point. It's the cosmic equivalent of firing a rifle to trigger an avalanche. But why would extraterrestrials do this? What purpose could justify manipulating stellar activity? One possibility: controlled experimentation. If their mission is to study how planets respond to geomagnetic storms and how those storms interact with seismic and atmospheric systems, they might prefer active experiments over passive observation. They'd want to create test conditions at will, producing storms of specific strength and timing to observe planetary responses. That's exactly how humans conduct science. We don't just watch natural phenomena, we reproduce them in controlled environments. Atmospheric scientists release chemicals into the ionosphere. Geophysicists set off controlled explosions to generate artificial seismic waves. Plasma physicists recreate miniature suns in laboratory reactors. If 3I Atlas represents a civilization millions of years ahead, it could be doing the same thing, but on a stellar scale, deliberately triggering solar flares to study Earth's reactions. This would explain the precise timing. It would explain why multiple X-class flares erupted in rapid succession from the same solar region, rare even during solar maximum. It would explain why the coronal mass ejections were so perfectly Earth-directed rather than randomly dispersed. And it would explain why subsequent seismic correlations were so exact, because they weren't coincidences at all, but outcomes of scheduled experiments. If true, the chain of causation would be staggering. Artificially triggered solar flare, targeted coronal mass ejection, geomagnetic storm, induced telluric currents, triggered earthquakes in critically stressed faults. Such a sequence would constitute an experiment in planetary physics of unimaginable scale and sophistication. The implications are chilling. It would mean earthquakes that killed people, destroyed cities, and caused human suffering might have been indirect side effects of extraterrestrial research. Even if their intent were purely scientific, the ethical consequences would remain devastating. It's the cosmic equivalent of human scientists experimenting on lab animals. We don't hate the mice or primates we study, yet they suffer and die for our pursuit of knowledge. From our perspective, the research is justified. From theirs, it's incomprehensible cruelty. Are we then the laboratory animals in someone else's experiment? The analogy is unsettling, but difficult to dismiss if artificial solar manipulation is possible. There are, of course, counter-arguments. The first, lack of direct evidence. We haven't observed 3I Atlas emitting energy beams or interacting with the sun. The November flares appeared natural in every measurable way, The case for manipulation rests purely on timing and correlation, circumstantial, not causal. The second, ethics. A civilization capable of stellar engineering should also have moral maturity commensurate with its intellect. Many xenobiologists and philosophers argue that long-term technological survival requires social stability, cooperation, and empathy, traits incompatible with reckless or malicious experimentation. A psychopathic species would likely destroy itself long before reaching interstellar capability. Yet both arguments have cracks. Absence of evidence isn't evidence of absence, especially when the technology in question could operate invisibly to our instruments, and ethical assumptions are projections of human morality. Alien civilizations could hold moral frameworks utterly unlike ours. They might value knowledge over individual welfare, or regard human casualties as statistically trivial. Hundreds of deaths from the November quakes are horrific to us, but for a civilization studying star-planet coupling across the galaxy, the loss might seem negligible, a tragic but acceptable data cost. Perhaps they see themselves as cosmic researchers, pursuing knowledge beneficial to countless worlds. This doesn't make their logic right. It only makes it possible. Their sense of ethics could be fundamentally alien, shaped by evolutionary pressures entirely unlike our own. A third, more moderate possibility exists. Perhaps 3I Atlas does have the capacity to influence solar activity, but does so cautiously, minimizing impact on Earth's biosphere. It might trigger only flares that would have happened soon anyway, adjusting timing for optimal observation. It might monitor Earth's seismic conditions and avoid interference when dangerous faults near major cities are critically stressed. In that case, the probe would be acting with maximum ethical restraint, balancing scientific goals with harm reduction. Or perhaps it doesn't consider human suffering at all, observing us with the cold detachment of entomologists studying ants. We simply don't know. And that uncertainty, hanging between benign science and indifferent experimentation, is what makes this possibility so profoundly disturbing. Chapter 8. December, the month of truth. As November gives way to December 2025, the attention of scientists, governments, and a growing portion of the public will turn increasingly toward the sky. The media, initially cautious and skeptical, will begin to publish more extensive stories about 3I Atlas and C2025 V1. Social networks will buzz with speculation, ranging from sober scientific analysis to wild conspiracy theories. Some governments will quietly declassify previously restricted information about interstellar observations. High-resolution photographs from military telescopes will reveal 3I Atlas as a dark, roughly spherical object with no discernible surface features at the available resolution. It will not resemble anything clearly artificial, no visible engines, antennas, or windows, but it will also not match any known asteroid or comet. Its form will appear too regular, its surface too uniform, C/2025 V1 being smaller and dimmer will be harder to capture in detail. The best images will show little more than a point of light, insufficient to determine shape or structure. Yet its trajectory will remain perfectly synchronized with 3I Atlas, maintaining that constant 9 million mile gap, as if the two were tethered by an invisible line. The James Webb and Hubble Space Telescopes will dedicate multiple orbits of observation time to both objects. High-resolution spectrograms will search for chemical or physical signatures revealing composition or intent. Infrared studies will look for thermal emissions that could suggest internal power sources. Planetary radar systems at Goldstone Observatory in California and other facilities will attempt to obtain echoes that might disclose surface properties or rotation. The results will be frustratingly ambiguous. Everything observed will be consistent with unusual but still natural interstellar asteroids, peculiar composition, anomalous dynamics. Yet nothing will definitively rule out an artificial origin. It will seem as if 3I Atlas was designed to be ambiguous, maintaining plausible deniability. If the object were wholly natural, detailed observations would eventually reveal unmistakable signs of geology or formation history. If it were artificial, clear technological behavior, radio transmissions, thermal anomalies, deliberate maneuvers would emerge, but 3I Atlas will display neither, remaining an enigma. Scientists will mark mid-December as a crucial date. Since it's perihelion on November 15, orbital models will show that around December 15, both 3I Atlas and C2025 V1 will reach optimal alignment for Earth-based observation. Their relative geometry with the Sun and our planet will provide perfect conditions to study magnetospheric interactions from multiple angles. Meanwhile, the Sun will appear to cooperate with the predicted scenario. A new active region, AR 4286, will rotate into view in early December, showing a complex magnetic configuration similar to AR 4274 from November. Space weather forecasters will predict a high probability of major flares by mid-month. If those predictions come true, and if the resulting coronal mass ejections, CMEs, are directed toward Earth, the November pattern will repeat. Intense geomagnetic storms during the very period when 3I Atlas is best positioned for observation, possibly followed by correlated seismic activity. Astrophysicist Avi Loeb, once ridiculed for his views on Oumuamua, will find a more receptive audience. In interviews and essays, he will argue that the coordinated motion of two interstellar objects is exactly what one would expect from an extraterrestrial mission, not from random natural bodies. Human missions routinely employ multiple craft, orbiters and landers, motherships and probes, telescopes and relays. So why wouldn't another civilization do the same? If we were sending an interstellar mission, Loeb will write, we wouldn't send just one spacecraft. We would deploy several specialized components to maximize the scientific return. What we're seeing with 3I Atlas and C2025 V1 fits precisely that mission architecture. Skeptics will counter that the absence of radio signals, the lack of visible structural features, and the absence of clear artificial maneuvers mean the extraterrestrial hypothesis lacks direct evidence. Orbital correlations, though intriguing, could have natural explanations still unidentified. Then will come the latest spectroscopic data, and the mystery will deepen. Astronomers using high-resolution spectrographs on the world's largest telescopes will analyze the reflected light from both objects. Spectroscopy, a cornerstone of astronomy, allows the determination of chemical composition by identifying which wavelengths are absorbed or reflected, each mineral or compound leaving its own fingerprint. The spectra of 3I Atlas and C2025 V1 will prove puzzling. They will show absorption features consistent with complex organic molecules, similar to those in carbonaceous asteroids and cometary nuclei, reasonably normal. But they will also display unusual near-infrared bands that match no known mineral or compound. Some experts will suggest these bands arise from minerals altered by cosmic radiation over millions of years in deep space. Others will propose exotic organic compounds not found naturally in our solar system, and a minority will venture a more radical idea that the spectral features could correspond to engineered materials, synthetic composites or alloys designed with precise optical properties. The artificial origin hypothesis for 3I Atlas and C2025 V1 will no longer be dismissed as pseudoscience. it will enter legitimate scientific debate. While astronomers debate spectral interpretations, another group will analyze temporal data, studying correlations between early November solar storms, the arrival of 3I Atlas and C 2025 V1, and a series of unusual phenomena beginning to surface. It will become clear that geomagnetic storms were not the only anomalies of that period. Multiple significant earthquakes were recorded around the globe within hours of peak geomagnetic activity. Emergency meetings will convene in capitals worldwide. Governments will ask, how should we respond? Should we issue public warnings about elevated seismic risk during major geomagnetic storms? Should 3I Atlas be classified as a potential security concern? Should humanity attempt communication? That last question will spark fierce debate. Some will advocate transmitting deliberate radio messages toward 3I Atlas, hoping to make contact. Others will argue strongly against it, invoking planetary protection principles. Until we understand their intentions, announcing our presence could be dangerous. But this argument will overlook an obvious fact. If 3I Atlas is intelligent, it already knows we exist. Earth has been broadcasting radio signals for more than a century. Our cities shine in visible and infrared light. Our atmosphere reveals biosignatures. Any species capable of crossing light years to reach us will already know we are here. As December progresses, discussions will intensify. Predictive models of geomagnetic seismic coupling will identify risk windows for late November and early December. By the time December begins, data from the previous period will still be under analysis. Preliminary results will suggest that several moderate earthquakes occurred within the forecasted windows at the end of November. Full analysis, however, will take weeks, requiring careful correlation between global seismic records and geomagnetic indices. Definitive results will not be available until well into December. Meanwhile, the scientific community will brace for what's coming. If mid-December solar activity unfolds as predicted, if geomagnetic storms strike during 3I Atlas's optimal observation window, and if subsequent earthquakes follow the established pattern, the cumulative evidence will become overwhelming. Dismissal as coincidence will no longer be credible. Then will come the inevitable question: are these correlations the sign of a newly recognized natural process, or something far more unsettling? Around December 10, predictions will begin to fulfill themselves. Region AR4286 will release its first major flare, an M9.1, barely below X-class. Solar physicists will watch closely, knowing that such complex magnetic configurations often trigger multiple eruptions in rapid succession. They will be right. In the days that follow, AR4286 will unleash a sequence of flares rivaling those of November. The associated CMEs will once again head directly toward Earth. The resulting geomagnetic storms will reach our planet just as 3I Atlas enters its optimal viewing alignment. The pattern will repeat, and with every recurrence, the question of the visitor's purpose will grow more urgent, impossible to ignore. Finally, an international consortium of space agencies, led by NASA, the European Space Agency, and their Chinese and Japanese counterparts, will decide to attempt deliberate contact. On December 20th, as planned, powerful radio transmitters at multiple facilities will beam coordinated signals toward the positions of 3I Atlas and C 2025 V1. The messages will be simple and repetitive, designed to be unmistakably artificial. Sequences of prime numbers, binary codes for physical constants, representations of atomic structure, and diagrams of the solar system. Greetings in multiple human languages will also be included, though few will expect the visitors to understand them immediately. Transmissions will continue for days. The world will wait in a tense mix of hope, fear, and fascination. News outlets will provide continuous coverage. Apps will send real-time alerts every time telescopes turn toward 3i Atlas, searching for a reply. Will any answer come, or will the cosmic silence continue, leaving humanity suspended between knowledge and doubt? Within days, the sun's predicted flares will erupt. The CMEs will travel toward Earth, arriving around December 15. The ensuing geomagnetic storms will strike just as 3i Atlas reaches its best observational position. If the pattern persists, and if seismic correlations recur, then in the days following December 15, Earth will experience earthquakes in its most active fault zones. Models will identify the window of highest risk between December 16 and 20. Seismic monitoring agencies will be ready. Emergency teams will remain on high alert. Scientists will track every signal, from seismographs and magnetometers to satellites and ground telescopes. December will become the month of truth. Predictions will either hold or fail. Patterns will either confirm or collapse, and humanity will learn whether it is witnessing a revolutionary discovery in Sun-Earth physics or being studied by visitors from the stars. The world will wait. Above us, the skies will hold mysteries on the verge of revelation, and throughout it all, 3i Atlas and its silent companion will continue their steady journey through the inner solar system, observing, measuring, perhaps experimenting. Answers will come soon, or at least deeper questions, more profound and transformative than any we have faced before. Chapter 9. Convergence and Understanding. As December 2025 moves toward its climax, humanity will find itself in a state of anticipation unlike anything in recorded history. It will not be panic or hysteria, but something quieter and deeper. A gradual realization that the universe is far stranger than we ever assumed. The possibility that we are being watched will shift from abstract philosophy to a serious scientific hypothesis, supported by a growing body of circumstantial evidence. The United Nations will convene an emergency special session to address the implications of the interstellar objects and discuss possible response protocols. For the first time, a global forum will meet specifically to consider the presence of potential extraterrestrial intelligence within our solar system. Delegates from 193 nations will listen to astronomers, physicists, biologists, and security experts outline what is known, what is suspected, and what remains uncertain. A cautious but transformative consensus will emerge. Most scientists presenting evidence will admit that, although there is no definitive proof that 3i Atlas and C2025 V1 are artificial, the combined weight of anomalies, synchronized motion, and spectral irregularities will make that hypothesis worthy of serious consideration. It will not necessarily be the most probable explanation, but it can no longer be dismissed. Astrophysicists will present detailed orbital analyses demonstrating that small non-gravitational accelerations and the precise maintenance of constant separation between the two objects are statistically improbable for independent natural bodies. Spectroscopists will discuss the unusual spectral features that do not match any known natural material. Space physicists will reveal the correlations between solar storms, the presence of the interstellar objects, and the resulting seismic activity. Seismologists, many of whom will have been skeptical of any link between geomagnetic activity and earthquakes, will present updated statistical analyses. With the November and early December data, correlations will have strengthened significantly. If earthquakes occur within the predicted windows, the likelihood of coincidence will drop below the level generally considered significant in science. That alone will not prove causation. Every student of statistics knows correlation does not imply it. But with plausible mechanisms such as induced telluric currents and piezoelectric effects, the evidence will gain substantial credibility. If the geomagnetic seismic connection proves real, its implications will extend far beyond the question of extraterrestrial visitors. Humanity will be able to develop early warning systems for earthquakes based on space weather monitoring. These systems will not predict exact locations or magnitudes, but they will identify elevated risk periods when tectonic faults, already critically stressed, are more likely to rupture after strong geomagnetic storms. Even modest predictive improvement could save thousands of lives annually. With a 48-hour warning window, people in seismic regions could take precautions, avoiding unsafe buildings, securing heavy objects, preparing emergency kits, mobilizing response teams. Imperfect prediction will still be far better than none. Yet the most troubling implications will arise if it is accepted that 3I Atlas might be influencing solar activity deliberately. If that proves true, the earthquakes of November and December will not be natural coincidences at all, but indirect results of extraterrestrial experimentation. This possibility will raise extraordinary ethical and security dilemmas. How should humanity respond to visitors who, even without hostility, may cause human deaths in pursuit of scientific study? And what power would we have to influence or stop them? The answer will be obvious. None. If 3I Atlas represents technology capable of interstellar travel or stellar manipulation, then it is vastly beyond our reach. Our fastest rockets would take months to reach it. Our nuclear weapons would likely fail to harm a structure built to withstand cosmic radiation and interstellar dust. Humanity will be, in practical terms, defenseless. Our only option will be communication, diplomacy, and the hope that any intelligence advanced enough to cross light years will also possess ethical sophistication enough to care about our survival. By mid-December, radio transmissions scheduled for December 20 will represent the most coordinated attempt to communicate in human history. Yet no one will know whether any reply will come. Even if 3I Atlas can understand, it may choose to remain silent, continuing its passive observation. As December progresses, the predictions will begin to unfold with uncanny accuracy. Solar flares forecast by physicists will occur. Active region AR4286 will produce multiple X-class flares between December 13 and 15, precisely within the expected window. Associated coronal mass ejections, CMEs, will strike Earth around December 15th through 16th, triggering geomagnetic storms rated G3 to G4, as strong as or stronger than those in November. Once again, the synchronization will be remarkable. Skeptics will still call it coincidence, but those who favor the hypothesis of deliberate coordination will see evidence of precision engineering, an interstellar mission observing a specific interaction between the Sun and Earth. On December 15, magnetometers around the world will record sharp fluctuations. The solar wind speed will surge past 530 miles per second. The interplanetary magnetic field will peak near 35 nanoteslas, and its BZ component will drop to minus 16 nanoteslas. The magnetosphere will open, and a flood of charged particles will pour toward the poles, painting auroras visible across 20 U.S. states and corresponding latitudes worldwide. Global media will broadcast the spectacle in real time. Commentators will speculate whether the visitors themselves are watching the light show, studying how Earth reacts to its star's fury. Then will come the true test of the model. will earthquakes occur within the identified windows. From December 16 to 20, seismographs worldwide will monitor every tremor. If significant earthquakes strike tectonically active regions during those days, the geomagnetic seismic link will become almost undeniable. If not, the model will face re-evaluation, but not dismissal, since earthquake occurrence is inherently probabilistic. While the planet awaits these results, December 20 will arrive, the date for the coordinated transmission. At 6 p.m. UTC, powerful radio transmitters at Goldstone, California, Parkes, Australia, and FAST, China, will beam synchronized signals toward 3I Atlas's coordinates. The messages will consist of prime number sequences, binary representations of pi and the fine structure constant, simple diagrams of hydrogen atoms, and maps of the solar system, clear signatures of intelligence, even if the content is not understood. For hours, transmissions will repeat across multiple frequencies. Sensitive radio telescopes will listen for any deviation in background noise. Hours will pass without response. December 21 will come and go. Then December 22. Still silence. Skeptics will claim victory, insisting 3I Atlas is nothing more than a natural object incapable of reply. But late on December 22, astronomers using the James Webb Space Telescope will detect something new. A faint infrared emission line corresponding to excited state water vapor, absent in all previous data. For a comet, such sublimation would be normal. But 3I Atlas will be moving away from the Sun, cooling. Why release vapor now? Some will argue for delayed outgassing from buried ice. Others will interpret it as deliberate, a subtle yet unmistakable signal, chosen precisely because it can be detected by our instruments. Over the following days, intermittent vapor bursts will continue, forming a pattern that analysts will describe as non-random. Cryptographers and mathematicians will search for meaning in the intervals, proposing that variations in timing or strength could encode data. Meanwhile, C/2025 V1 will remain silent, showing no comparable activity, continuing its synchronized flight in enigmatic calm. And on Earth, seismographs will tell their story. If the November pattern repeats, several moderate to strong earthquakes will strike between December 16 and 20, in Vanuatu, the Philippines, or along the Iran-Turkmenistan border. If all these events fall within predicted windows, the supporting scientists will feel both vindicated and unnerved. With 2 complete cycles, November and December, the statistical evidence will become overwhelming. Though causation will remain unproven, the hypothesis that geomagnetic storms can trigger earthquakes in critically stressed faults will gain remarkable scientific standing. Yet the deeper question will linger. Are these storms natural solar events or controlled phenomena artificially amplified by 3I Atlas as part of an experiment? As December draws to a close, the trajectories of 3I Atlas and C/2025 V1 will carry them steadily away from Earth. By January 2026, they will begin their outward journey beyond the inner solar system. By February, only the largest telescopes will still track them. By March, they will vanish into the darkness. Will this be humanity's only opportunity to engage with alien intelligence, or merely the first of many? If systematic galactic exploration exists, our solar system could receive visitors regularly, perhaps every century or millennium. 3I Atlas may simply be the first we have detected. Historians and astronomers will re-examine past records, the Great Comet of 1680, the Tunguska event of 1908, for possible precedents. Most will dismiss such speculation, but the very act of rethinking history will illustrate how profoundly 3I Atlas has altered human perception. The extraterrestrial hypothesis will no longer be taboo. It will become a legitimate question for empirical inquiry. By early 2026, the geomagnetic seismic model will issue new forecasts predicting elevated risk for late January and mid-February. Researchers will publish them openly, reasoning that potential benefits outweigh reputational risk. Whether or not future predictions come true, humanity will have changed. We will have crossed a psychological threshold. We will recognize that we might not be alone, and that we are part of a cosmos filled with other minds. This awakening will bring awe and fear in equal measure. Philosophers and theologians will wrestle with implications. Religious traditions will adapt or struggle. Secular thinkers will question meaning and morality in a universe rich with intelligence. Public surveys will show a dramatic rise in belief. By late December, over 45% of people will believe intelligent extraterrestrial life may already exist in our solar system, up from less than 10% before 3I Atlas. The shift, and as 3I Atlas and C2025 V1 continue their voyage toward the stars, they will carry their secrets with them. Perhaps future generations will find them again, or encounter others who will reveal their intent more clearly. For now, in this critical December of 2025, humanity will stand suspended between knowledge and ignorance, between arrogance and humility. We will watch the skies with new understanding, observe the sun with heightened attention, and study Earth itself with renewed awe at its interconnectedness. The solar storms, the auroras, the distant tremors, the mysterious arrivals, all will converge into a greater understanding. We will not yet have all the answers, but we will be transformed by the questions. December will not end with apocalyptic revelation or confirmed contact, but with something subtler and deeper, a shift in worldview. We will no longer assume we are alone. The cosmos will have expanded within our minds, and as 3I Atlas fades into the cosmic dark, it will leave behind not answers, but the most precious gift of all, questions that will reshape our science, philosophy, and identity for generations to come. The universe will prove vaster, stranger, and more wondrous than we ever imagined, and we, witnessing this moment in human history, will stand at the dawn of a new age of cosmic awareness.